Hey guys, so today we're going to be talking about gradient descent and how they relate to neural networks. And I've kind of tried to make this video a couple of times, but I've been a little bit burned, and so I'm not even going to go into the presentation because that's what caused the problem last time. So I'm just going to go through this as is right here. So as you can see, it's kind of being a little bit lame. I'm just going to take that off. So what is a gradient? Mathematically, when we're talking about a gradient, we're talking about the gradient of a function. And what that is it is the partial derivative of that function with respect to whatever the variables of that function are. So if we have this function of x and y, then the gradient of f is going to be the partial derivative, the vector that is formed when you take the partial derivative of f with respect to x and then the partial derivative of f with respect to y. And so if this function happened to be a function of x, y, z, then you would also put in here, sorry, my handwriting, the partial derivative of f with respect to z, and what that allows us to do is say, if we have a level curve, so that would be, maybe some gradient. Well, let's just move on to my next slide so you can see this. I just wanted to point out that the gradient is always normal to a level curve, and so you'll see what that's talking about. Here we have a level curve, and what I wanted to demonstrate here is that a lot of people, when they look at this, they might see, okay, these are the maximum, and so I think that this is going to be the gradient, right? Because that would kind of make sense. It's the most uphillish. But really, you want to look at the very point that you're at, and there's where you want to calculate the gradient. Not the direction to the greatest maximum, but the gradient at the very location you are. And so you're going to do that by finding the line that's tangent to the curve where you are, and then you're going to find the vector that's orthogonal to that, right? And so that just means that it's at 90 degrees. And so what that's going to tell you is that if you move in this direction, that's the steepest incline. Okay, and so maybe it's not going to be the steepest incline over here or whatever, but at this very point in this direction, that's the steepest incline. So that's just kind of gradient, and now I kind of want to talk about neural networks in a really high-level way. So this is probably an image that if you've ever heard about neural networks, this is what you've seen, where you have some set of inputs over here, and you have this layer of neurons, and then you have some output, and in between you got all these lines and stuff. And so I kind of want to explain what those lines are. And so when we think about the brain, how it learns, and that's kind of what we're trying to mimic, is that it has neurons, and these neurons will receive some input, and they will fire to their connections with other neurons, and we hear about some of those connections being strengthened or whatever. And that's, have you ever heard a teacher say that, where if you do repetition, you're strengthening those neural pathways? And that's how you're learning. And so we want a way to be able to connect the inputs to some, we'll call them neurons or perceptrons, and then have connections between neurons, right? And so that these arrows just kind of represent those connections, and all that's happening is I'm sending that input to that neuron, and then that connection is going to have a weight associated with it, and that's how we're going to be able to strengthen that connection or weaken a connection. Maybe there's a situation where a particular input isn't very helpful for predicting a certain part of something, or for learning a specific part for something. So maybe you want to weaken that weight, that connection. And so then you're going to have this B here as a bias, and that's just one other way to tweak how those connections are interacting. And then you have some activation function here that, once you've applied these weights and all of these connections and this bias, you can have some number, because all you're going to do is add up all of these weights and all of these numbers, and they're going to go in here, and you're going to add that bias, and you're going to have an activation function. And what that says is it's going to take in that number, and then it's going to basically give you, a lot of the times it's either a 0 or 1 or something kind of like a step function, where if you meet a certain threshold, then you activate, basically. And that's why it's called an activation function. And there are other functions that they use, not generally step functions. So this one's called a sigmoid, where it kind of looks like a step function, right? But there's actually also, right here, it's not straight up and down. It's got some what's it called? Some slope, and that slope's going to allow you to make some changes and get some more insight than just a 0 or 1 would. But we don't want to go too deep into that. But anyway, so, and then you're going to go kind of through this whole thing, and you're going to go to the last one. You're going to be applying weights to every single connection, and there's a bias to every neuron, and there's an activation function, and eventually you're going to get an output. And that output is usually going to be something between 0 and 1, so it could be like a 0.60. And let's say you're trying to predict whether somebody's healthy or not. And so all you have is 1 is healthy, 0 is unhealthy. And let's say your output is a 0.60. And so what that would mean is that you're predicting healthy, right? But a 0.60 isn't a 1. You know, it's a it just means, you know, it might be considered a confidence, where you say, you know, I'm not super confident, but I think they're healthy, is basically what this network is saying. And then the question is, how do you improve upon that? We do that with a loss function. And so this is when the calculus comes back in, because essentially what we're trying to do is optimize this loss function so that we have as little loss as possible. And what that's going to do is drive this up from 60 to 0.9 to 0.99 or whatever, you know, so that our confidence is really high and we can make more accurate predictions. And so essentially what you're going to do is you're going to take the partial, you're going to calculate the gradient of that loss function so that you can move in a direction that is opposite the gradient, right? Because if you're moving with the gradient, you're going up, and we want to minimize loss. So we're going to go in the exact opposite direction, because that's going to be the direction that's going to, we know for sure that's the fastest way from that point to go downhill. And so the way you do that is by taking the partial derivative of the loss function with respect to these weights and biases. And so yeah, without going into the math too much, that's kind of the high level that we want to be at. And I just wanted to kind of do one of those stereotypical drawings that you might see. I pardon me for the roughness, because I'm not actually in the present mode. But you know, one of the ways that you typically see this is that you have some function, and you start off in a random place because you're randomly going to assign those weights and biases when you start off, because you have no inclination at the beginning as to what's going to happen. And so you're going to wind up in a random place, and what you're going to want to do is move, that's just, the gradient's going to be the steepest way, right? And so you're going to want to go in the exact opposite of the steepest incline, and that's going to ensure that your loss function is going down, because that's what this line is, it's the loss. And you want to get to this global minimum right here, because that's going to mean that your loss is minimized as much as possible. And so, you know, you can imagine this being a ball, and you just want it to roll downhill. And so you're going to see what the gradient is, and you're going to take a step based on something called a learning rate. And so that step could be big or it could be really small. You know, if you're really small, it might just take a really long time to get there because you're kind of idling along. If it's way too big, maybe you overshoot it and you come over here or something like that. And again, this is all done by calculating that gradient, just like we've done in calculus before, and then going back through this, it's called backpropagation, back through this neural network once we know what the output is, and we can go along all of these connections and adjust those weights and biases so that we can improve our neural network. So then if we're back at this topographical map, let's say that these are minimums, so let's say that's 100, and this is 200, and this is 300, or whatever. So we're going to start off in some random place here, and we're going to calculate the gradient at whatever this place is, and kind of move along here. And you know, at times it might seem like you're kind of meandering, but we know that because we're calculating the gradient, we're always moving downhill, and eventually we will get to that that minimum, right? And so maybe it's not the most direct path, you know, because we're going kind of squiggly here, but we know we're going to get there. Okay. So I wanted to give one example, and so I'm going to be using the MNIST dataset. What that is, it's just a dataset of handwritten letters, and they're kind of formatted in this way where the numbers, they're numbers, and they're always centered in a square. And so what we're going to try to do is we're going to use this data set that has 60,000 or something handwritten numbers, and we're going to try to eventually be able to give it a handwritten number and have it predict what that number is going to be and be correct. And so the first question is what are the inputs? And so in the simplest network possible, all we're going to do is take each pixel of this entire thing as an input, and you would say, if it's not part of the written thing, then it's a 0, and if it's part of the written number, it's a 1. And we're just going to take that entire picture and kind of turn it into an array of zeros and ones. And so I wanted to show you kind of how easy it is to do this in kind of modern languages. So this is Python. I'm just in a Python notebook, and there's a language called TensorFlow, and it's kind of got this extension Keras, which has this data set in a really easy to use format, and you can just load it in, and essentially what you're going to do is you're going to flatten that image into an array of size however many pixels there are. So there's 784 pixels, so that's just how big the array is. And then you're just going to feed that into a network, and so all this is doing is creating a network that has a couple of layers, and each layer has a particular amount of nodes and a particular activation function like we were talking about. And then this has a loss function, and that's what we're going to be optimizing, is that loss function. That's categorical cross entropy, and that's just one of the loss functions that there is. And then you can just fit it, and it's really that easy. And what that means is that you're going to be able to run this kind of, and what this is just it's trying to kind of calculate, go through and look at the different data in the data set, and then back propagate through the network to improve it. So it's doing all of those calculations, and at the end, this really only took a couple seconds to train. We have this 93% accuracy, and so just as an example, I gave it this part of the data set that it had never seen, and I just chose a random one of them for it to predict, and it predicted that it was going to be a 0, and this y-test show is just saying this is what it really was, so it really was a 0, and just to make sure, I pulled up the image, and it was in fact a 0. And so you can see, even with this really simple network that's just taking in each pixel as its own input, it can do some really smart things. And so obviously there's some better ways to do it. If you know anything about neural networks, you can do a convolutional neural net that's going to be a lot better at handling images. But for something so simple like this, this is really all you need. But anyways, so that's neural networks and gradient descent and how they relate. Thanks.